Welcome to Group 1 aspirants. Today we are going to learn about the nuclear energy. So before going to nuclear energy, let me give you a simple introduction to this. We all know that negative energy charged particles, positively charged particles attract each other, right? This is one thing so it will attract each other. So this is what is going to happen, and we all know that the positively charged particles, two positively charged particles will actually repel each other, right? So this is the case. We know that negatively charged means it is electron. What is that? It's electron. And positively charged means it is proton. Okay, and neutral, we know that neutrons will have no charge for this neutron. So you all know that when two protons come together, or when they come together, they repel each other. So this is the thing we all know, everyone knows about it. And let me give you one more thing. So what is an atom? We all know that atom is it looks like something like this. Let us take an imaginary atom. So every atom consists of a nucleus. What it is? Nucleus. So around the nucleus, we all know that the electrons will revolve. So electrons revolve around the nucleus. And the nucleus consists of what? Nucleus consists of protons and neutrons, isn't it? This is a very clearly everyone knows this. Now my question is, if two protons repel each other, then how these two protons are together in this place? That is an important thing that we need to understand. What are the forces that are actually binding these protons together in this tiny place called nucleus? So right? So if these two repel each other, but they are kept together by a huge force, something bigger force. So what is that big force is called? So that big force is called nuclear forces. This forces is called nuclear forces, isn't it? So these nuclear forces will actually keep these protons and neutrons together in this particular place called nucleus. Now let me give you one more this thing. So when you break this nucleus into two or more, what happens? What should happen? Since two protons are kept together by force, if you break these two protons separately, if you separate these two protons, obviously it might release the energy, right? This is one aspect that we should understand. So it would release the energy. That is a clear thing. So what I would like to say here is, if there are protons out there, let us take 238 protons are there in a nucleus. Okay. Out of this 248, I will divide this into two parts. One is, let me give you 164, something like that. So it's how much? 8 and then 12 and 3. Okay, 100. Sorry, it's not 100. I'll take 208 divided by 2, that it gives 1 and 9. So 119 plus 119 will actually gives you two nucleuses. One nucleus 119 and another nucleus 119. What I would like to say here is, if you have taken 238 protons are kept in one place in a one nucleus with huge force, And these 238 protons are now divided into two parts, 119 plus 119. This is an imaginary thing, just I am trying to build you a concept. So if I do this, what actually happens here is the energy that is binding these protons are actually released. So that energy will be released into the outside, right? So that is the one thing that I would like to say. And then another thing is, we all know that Einstein and Einstein's formula, that is E is equal to mc square. M is nothing but actually a delta M, which actually say what actually this formula says is, this formula tells us the mass is actually converted into energy. What actually this says, mass will be converted into energy. So which means if a mass, some mass is lost, and then the lost mass will be converted into energy. So if you break this, we are talking about this breaking, if you break this, then there may be a loss of some sort of protons, some sort of neutrons might lose here. So that last mass is actually can be converted into energy. So that energy is also called E is equal, that is E is equal to mc square formula. With this we can say this. So now you are clear that there are two things. One is E is equal to mc square, that is the mass is converted into energy. So if you lose an mass in a particular nucleus, then that last mass is actually converted into energy. So that is the one thing that we should always remember. What I would like to say here is, if you look at this, so what I would like to say here is, if you look at the nucleus and all, the nucleus will have certain number of protons and certain number of neutrons. So if you calculate the masses of each neutron in that nucleus, and if you calculate the mass of each proton mass and you combine these together, that mass will be higher than the nucleus mass. So that means the nucleus mass is, let us take x, nucleus mass is x, but mass of all protons plus neutrons is y. So here the mass of these individual protons and neutrons value is always greater than the mass of the nucleus. That means when nucleus formed, the mass has, some mass has lost. So that last mass is converted into the energy, and that energy is called nuclear energy. So that energy is called nuclear energy. So that nuclear energy is responsible for keeping these protons and neutrons together in that nucleus. So here the nuclear technology is a technology that would help tap this energy, and then if the technology that would help to tap this energy is called nuclear technology. So today we are going to deal with this nuclear technology. So India is the only developing nation to have indigenously developed, demonstrated and deployed nuclear reactors for electricity generation. I will tell you how this electricity is generated. Okay. So what I would like to say is, the only developing nation to indigenously develop and demonstrated and deployed these nuclear reactors for electricity generation. We also call this as a civilian purposes. Most of these developed countries will deny this technology to us. Since they have denied this technology, we have developed ourselves. So this was made possible through several decades of extensive scientific research and technology development, primarily in an organization called BARC. So in this regard, Dr. Homi J. Bhabha was the architect for this. The country has a nuclear ores which a total of about 78,000 tons of uranium metal and about 5,18,000 tons of thorium metal can be extracted in India itself. Now before going into this nuclear technology, let us try to understand the nuclear fission. The nuclear fission is the process of splitting a nucleus into two nuclei with small masses. This large mass is actually splits into a small mass atoms, and then it is also produces energy, as we have already discussed this. Fission here means to divide. Remember that the fission has two S, therefore it splits into two parts. Okay, two S's means two parts. Just to remember that we are giving this. Okay, so small atoms, small atom 1, small atom 2, that's why two S's and two parts. So fission reaction, and there is a so that you don't have to confuse with the fission and fusion. Fission means divide. SS, two SS, two double S, small atom 1, small atom 2, so splitting. So that's why when it splits, the energy is released, and that energy is utilized for peaceful purposes. And there is a fission reaction here. Only large nuclei with atomic number above 90 can undergo fission reactions. So fission reactions, not every atom would undergo these fission reactions. It's only atoms with atomic number 90 and above would undergo fission. Atomic number 90 means the nuclei will have 90 protons in that. The products of fission reaction usually include 2 or 3 individual neutrons. The total mass of the product is somewhat less than the mass of this uranium-235. We all know that very famous thing, uranium-235 is the fissile material. So when this fissile material, uranium-235 will undergo this fission reaction, and it will produce 2 products. So in this 2 or 3 individual neutrons also. Okay, it may be 2 or it may be 3. So why I am calling 2 or 3 is it is in between 2 or 3. That is why it is called 2 or 3. Here if you look at this, low speed neutron, when this low speed neutron is captured by the nucleus, that means when a nucleus is hit by another neutron, then that neutron will actually splits into 2 particles, 2 small size atoms, and then it also releases 3 neutrons. It also releases 3 neutrons. So these, it may be 3 or it may be 2, is anywhere between 2 or 3. So these 3 released neutrons will actually again hit the another neutron of uranium-235. So that means if a single neutron helps to split a single nucleus, and then another 3 more nucleuses will be split by this. So 1 will become 3, and 3 become 9, and 9 become 27, like that. So that means if you start this reaction by 1 neutron and 1 nucleus, splitting 1 nucleus, then it will actually create a chain reaction on this. Chain reaction on this. So this chain reaction will actually, so if you start this, it will actually create a chain of reactions for this. So the chain of reactions are uncontrollable, because each a small 1 gram nucleus, 1 gram of uranium will consist of millions of atoms in that, right? So it will create a chain of reaction which will not be controllable. So if it is not controllable, it actually releases huge energy, right? So that reaction is called chain reaction. So a chain reaction is an ongoing series of fission reactions. The billions of reactions occur each second in a chain reaction. As we were talking about that, one neutron colliding one nucleus, and this one nucleus will produce another 3 neutrons, and these 3 neutrons will produce another, each neutron will produce another 3. It is like that, like 1 and then 3 and then 9 and then 27, like that it will actually keep producing. So this is called a chain reaction. A neutron is about to hit this nucleus of a, here you see here, a neutron is about to hit the nucleus of a uranium atom here. So this one. So once this is hit, it actually releases energy as well as 2 more atoms, and these released neutrons again hit another atoms, and these atoms again it will create another 3 more like this. So like that it continues. The billions of reactions occur in each second in this chain reaction. Okay, so on the earth, nuclear fission reactions take place in nuclear reactors. So this reaction will actually take place in the reactors. So the reactor would look like this. So which in these nuclear reactors, what we need to do is we need to control this chain reaction so that we can generate electricity. What we have to do is, see this chain reaction, if chain reaction continues like that, it generates huge energy. That huge energy, we cannot control that energy, obviously it will burst. So if it bursts, that we cannot, it's not possible for us. But if you control that chain reaction in a specific manner, then you tap that energy so that that energy is used for electricity generation. Okay, this uncontrolled chain reactions takes place during the explosion of an atomic bomb. We all know that this is a simple example. If uncontrolled, if the reaction is not controlled, it will explode like a atomic bomb. We all know that atomic bomb actually runs on this principle itself. So we all know that kind of danger thing that it can create if it is uncontrolled chain reaction. So what you need to do is you need to control this chain reaction. So it's good, sir, we will control this chain reaction. So then what are the products of these fission reactions? What are the products that comes out of this? The products of these nuclear fission reactions are radioactive. But energy released from these reactions is less harmful to the environment than the use of fossil fuels, that you have to remember this. The products are intensely radioactive and must be treated or stored in a particular manner itself. So radioactive materials, that are products that are generated in this fission reaction, are stored carefully. Treated, stored carefully. That you need to remember this. You know, one decay time, that is decay time is like a 7,30,218 years. So that means a nuclear with the decay time, that is off life period. Let's not get into that, but off life period is a very high for certain radioactive materials. So, and there is another important reaction called nuclear fusion. So nuclear fission is the combining of 2 nuclei with low masses to form the one nucleus of large mass. The nuclear fusion reactions are also called thermonuclear reactions. What is called thermonuclear reactions? Here it is ulta. It's something like 2 small atoms will come and form a large atoms. In this process also it loses energy, mass. So that last mass is again converted into the energy. How to remember? Don't confuse with the word fission and fusion. Here in the fission, I told you about 2 small atoms. Here only 1 S, so one single atom. So that is why this is called fusion. Fusion means 2 combining 1. Here 1 combining 1 giving 2. So that you need to remember. These fission reactions exist in the stars. We all know that our sun is a good example of a thermonuclear reaction. Sun, it's almost impossible to create fission reactions on Earth, since they need temperatures above 1 million degrees centigrade in order to take place. It is not easy to combine 2 atoms and form another one. For that you need a huge temperature, like temperature is 1 million degrees centigrade. That is almost impossible to do that. So the nuclear fission reaction produces less nuclear waste than the nuclear fission, and the materials are easier to obtain. That you need to remember this advantage of this. So when deuterium and tritium will actually combines together, and it actually gives helium and neutron. Helium and neutron, or we all know that helium is a very not harmful material, right? Not harmful. It's not at all harmful. But in the fission reaction, the products are radioactive in nature, but here it is not that. That you need to remember this. And here the mass of this deuterium and tritium combined together is higher than the helium and neutron atom. So that means some energy has lost, some mass has lost here. So what is that mass? Last mass is converted into energy with the help of this formula. So that you need to remember. So only large nuclei with atomic number above 90 can undergo fission reactions. We have learned this. So the products of this fission reaction usually include 2 or 3 individual neutrons. The total mass of the product is somewhat less than that mass of this uranium-235. We all know that. Now let us look into this important thing called bark. Dr. 𝗵𝗂 established this atomic energy establishment at Trombe in January 1954 for multidisciplinary research program essential for the ambitious nuclear program of India. After the sad demise of this 𝗵𝗂, 𝗳𝗏𝗔𝗵𝗂 in 1966, AEET was renamed as BARC, that is 𝗵𝗂 Atomic Research Center, BARC. So yeah, before going into this, let me give you one more how this electricity is generated. So we have understood that when 2 atoms combine, energy releases. We have understood that if one atom splits into 2, that also releases energy. Now, how this electricity is generated? Let me give you an example of that. See, if you want to generate an electricity, what electricity is generated by actually, by rotating the turbine, we generate electricity. Simply you understand this. By rotating the turbine, we generate electricity. So this is one thing that you remember. So if you want to rotate the turbine, how you rotate the turbine? In order to rotate the turbine, what we do in all these things, the best example is power plants. Power plants like electricity produced using this river water. So what we do in the river water is, in the river water, the river flows. With the help of that flow, what we do is we actually revolve the turbines. As the turbines revolves, as this using this flowing water, then that flowing water will actually revolve the turbine. That turbine will actually generate the electricity. So this is the thing that we need to do. So instead of using this flowing water, What we can also do is we can also produce the steam. The steam will also revolve the turbine. So how do you produce the steam? For steam production, we need heat. So that heat is actually generated either by using the coal. That's why thermal power stations has come. If you generate that steam with the help of nuclear reactions, then you call this as a nuclear reactions, nuclear power plant. So these are the two areas that you need to understand. So what we are going to do is we actually use the steam, and then the steam is used to revolve the turbine, and then the revolving turbine generates electricity. So how you produce this steam is a different thing. If you use this coal for producing the steam, that would revolve the turbine, then we call this as a thermal power plant. If you use the nuclear reaction to produce the steam that would produce the electricity, then we call this as a nuclear power plant. So let us look into this nuclear power plant of India, and then we'll look into this, the technology behind this also. So before going into this, we have learned that India contains, the natural resources of India contains uranium and thorium. So uranium is the immediate material that is used for producing power. We all know that. But what about the thorium? We know thorium, we have thorium resources, very high, huge resources, right? So what we have come up with is, in order to use this thorium also, so what India has come up is, India is coming up with a nuclear cycle where one nuclear plant, stage 1, we will produce the nuclear power, and then the byproducts will be again utilized for another nuclear power, and then that is also used for another nuclear plant. Like that, we have 3 stages of nuclear cycle, and let us look into this nuclear cycle one by one. So the goal of this 3-stage Indian nuclear program is resource sustainability, which means accordingly the power generation in the 3rd stage is predominantly dependent on the thorium based fuel itself. The thorium is again produced in the 2nd stage itself. So this is in the first stage, stage 1, we will use this pressurized hot water reactors, that is called PHWR, and then we will use, in the 2nd stage, we will use FBTR, that is fast breeder reactors, and then advanced heavy water reactors. These are the reactors that we use in various stages. We will learn one by one about all these things individually. Okay, here you can see in this stage 1 we will be using natural uranium, and the uranium fueled pressurized hot water reactors here, and we will be producing a 300 gigawatt electricity a year with this. And then the byproduct that comes is uranium and then plutonium, and then uranium and plutonium is again used in as a fuel here, and then this, we will learn this one by one. Here we would like to produce 40 to 1000 gigawatt electricity per year at this 2nd stage, and then in the 3rd stage we will use this much gigawatt electricity in the 3rd stage. Okay, so power generation is primarily by this the PHWR building fissile inventory for stage 2, and this stage 2 will actually expanding the power program, building this uranium-233 inventory, uranium-233 produced here. So let us look into this one by one about this current status of Indian 3-stage nuclear power program. In this current stage, the stage 1, we have PHWR, that is 18 reactors are operating in this. 18 reactors are operating in this 4 by 700 megawatt electricity under construction. That's 700 megawatt electricity produced reactors, 4 reactors are under construction. The several others are planned and gestation period has been reduced. So gestation period means the period when you start the constructing the reactor and then producing, stabilizing that reactor is called gestation period. This gestation period has been reduced drastically. Here for this product, the power potential with this is 10 gigawatt electricity. Okay, and then 2 BWRs are also operating. 1 VVR also achieved criticality. Criticality means that has stabilized, that reactor got stabilized. Thank you.